Hello, you want to model a new heat transfer problem by UMATH subroutine in Abaqus. In this video, we are going to teach you how you can do it easily and quickly. UMATH subroutine is a subroutine to define a new thermal behavior, property for your material. And as you can see in this image, you can get temperature gradient and thermal behaviors for your material. To understand how to do that, stay with us in this video. We have actually prepared for you a training package, a tutorial package, a UMATH subroutine in Abaqus package. In this package, first we explain the formulation, the heat transfer formulation. Then we explain the UMATH variables, the inputs and the outputs in the video. We explain the UMATH subroutine line by line, how to write it for the beginners. And the Abaqus model to run the UMATH subroutine is explained step by step in another video. And result extraction, how to get the results, is explained also in details. And in this package, you can download all Abaqus and UMATH subroutine files. So you will have all files and trainings. You can work on them, you can change them, improve them, and run them and get the results. In this package, you will get one example, which is example number 1, in which a simple UMATH subroutine is explained to you to understand. In this example, most necessary details are explained to you. And in example number 2, which is a medium UMATH, we are explaining more details in a more complex UMATH. By downloading and actually understanding this package, you will be able to write your own UMATH subroutine in Abaqus. You can download this package by the link in the description. Or instead of downloading a training package, we can write your UMATH subroutine and do your project. We will prepare a package for you. All your problem and your project formulation will be explained to you in the videos. And after that, we will prepare a tutorial videos for the UMATH subroutine, and we will explain the UMATH subroutine with your formulation to you. We will actually test the UMATH subroutine by published papers, and we will explain it to you in another videos. So you will get a package for you in which all the things you need to actually do your project is included. You can order your project by the link in the description again. Thank you for your attention.
Hello, you want to learn UMATH subroutine in Abaqus easily and quickly. UMATH is a subroutine to define a new mechanical behavior for materials. Stay with us. The first question, which is very important, is that why UMATH? Why we need UMATH subroutine? Consider you have a sample and you want to apply load, and by modeling and simulating, predict the mechanical response of this sample, predicting the stress strain curve. The first strategy is that you have some of the points of your stress strain behavior from lab or from published experiments. You can easily go to the Abaqus, to the property, define a new mechanical behavior, plastic behavior, and enter those points like this. This is the simplest way of solving the problem, but it is not precise because Abaqus interpolates between these points and solves the problem in all points. If you want to solve your problem more precisely, then you need to have a constitutive equation, a constitutive behavior for your material. An equation in which the stress is a function of strain, temperature, and strain rate. In this example, we have equation, we have a material obeys this equation, which is Johnson-Cook equation. Again, if you have the constitutive equation which is well known and included in the Abaqus, you can go to the Abaqus, again go to the property, define a material, and instead of entering the points, you can define the behavior and enter the parameters and constants of your model. Here it is Johnson-Cook model. It is more precise solution because you have an equation for all your points. But consider you have a material or a new material or a new constitutive equation. The equation between stress and the components is very new, which is not included in the Abaqus, and you don't have points. So what you can do, then you need a place to write this equation or your equations and define the Abaqus that obey this behavior to solve my problem. This is the reason we need UMATH, because our equation is new. The next important thing about any subroutine, especially UMATH, is UMATH inputs and outputs. UMATH is a machine, accepts some inputs, process on inputs, and exports the inputs as an outputs. UMATH has some variables: stress, strain, DDS, DDE, and some of the variables you can see here. Actually, all these variables are being computed in the Abaqus, transferred to the UMATH. In the UMATH, we need to write some equations based on our constitutive behavior to recompute these variables, all the variables, and return back all these variables to the Abaqus. This is how Abaqus and UMATH interact with each other, which is necessary to write a well-working UMATH. Here, for an example, we explain one of the most important variables of UMATH, which is DDS, DDE. Consider you have a stress and a strain at this point, and you want to compute or predict the stress at the next point. How you can do that? The first thing comes into the mind is that you have the slope of the diagram. If you have the slope of the delta stress with respect to delta strain, then you can linearly solve this problem and predict the stress at each point. So if you have a stress as a function of a strain, then by making a derivative, you can define the DDS, DDE for your formulation. So we call this slope of the diagram DDS, DDE. This is the nature of this variable. For all variables based on your equation, you need to well understand the nature and the source of the variables. For example, in elastic regime and for elastic problems, the elastic stiffness matrix is DDS-DD matrix. We say that you can learn UMATH easy and fast, but is it really possible to learn UMATH in a week? If yes, how? UMATH has many details, many variables, but do you really need to know all details to solve your problem? Of course not. Only necessary aspects are enough to solve your problem. UMATH has many details. If you want to learn all details, maybe you will need more than 5 years to be an expert in UMATH writing. But in your problem, no. Maybe in your equations, only 3 of them are enough for you. So you can save your time and save your energy. To this end, we have prepared a UMATH training package for you. This package includes some videos. A video explaining the formulation, all the constructive equations. The next videos explain UMATH variables, something like I explained the DDS-DDE. Another video explains whole UMATH line by line, how the formulation converted to UMATH codes. Any UMATH needs to be solved in Abaqus software, so the Abaqus models actually are explained step by step in another videos. At the end, the result extraction and comparing with the experiments is explained. All Abaqus and UMATH files are also included in this package by downloading. This package includes 3 examples. Example number 1, which is a simple UMATH, only most necessary details are explained for beginners. Example number 2, which is medium UMATH, more details are explained to be more expert. And example number 3, which is a complex UMATH, all details are explained for advanced users. You can simply download this package and use it to learn UMATH easily and quickly by the link in the description or from the website, our website FEAassist.uk. You need more, you don't have time, you don't want to learn every aspect, and you want your UMATH to be written sooner. Okay, we can write your UMATH, test it, verify it with published results, and teach it to you with videos and meetings. So you can order your project also by the link in the description or the website FEAassist.uk. Thank you for your attention. Hello, you want to learn FEAuMATH subroutine in Abaqus easily and quickly. UMATH is a subroutine to define a new mechanical behavior for materials. Stay with us. The first question, which is very important, is that why FEAuMATH? Why we need FEAuMATH to solve our problem? Consider you have a sample and you want to apply load for that in a dynamic way and predict by modeling and simulation the mechanical response, the stress-strain behavior, or the load displacement curve. The first strategy is that you have some of the points of your stress-strain or load displacement curve from the lab or published experimental results. Then you can easily go to the Abaqus property, define a new material, go to the plastic behavior and enter those points like this. Abaqus interpolates between these points and predicts the behavior of the material in all points. This is the simplest way, but it is not precise because of interpolation. If you want to solve your problem more precise, then you need to have the constitutive behavior or constitutive equation of your material. Your material mechanically obeys some rules. If you have equation and the equation is included in the Abaqus, then you can go to the Abaqus again to property, materials, mechanical, and instead of entering the points, define the behavior. For example, here it is a Johnson Cook. You can enter the parameters and constants of your equations. Abaqus will solve your problem in all points based on this equation. This is more precise because you have equation. But if you have a new equation for a new material, new constitutive equation, and the equation is not included in the Abaqus to enter the parameters and constants, then you will need a place to write your equations and force the Abaqus to solve the problem based on your equations. This place is FEAassist subroutine. The important thing about the FEAassist subroutine learning is UMATH actually inputs and outputs. FEAassist inputs and outputs. FEAassist has some variables. Some of them are inputs from the Abaqus. In FEAassist we process on the inputs and export the processed inputs as an outputs. Actually, these variables are computed in the Abaqus. The old values or the initial values transferred to the FEAassist. Into the FEAassist we need to write a new equation or some new equations to redefine these values, and the new values of the variables return back to the Abaqus. This is how Abaqus and FEAassist interact with each other, which is necessary to understand to write a good working FEAassist. Here we explain one of the most important variables of FEAassist subroutine, which is stress, and here stress new. Consider you have a stress and a strain at this point, and you want to predict and compute the stress at the next point. What you can do? In a dynamic way, the strategy is that the new value is the old value plus the derivative function, which is the function of the slope of the diagram and the incremental amount of the strain, as you can see here. For example, in elasticity and elastic problems, the slope is elastic modulus or elasticity stiffness matrix. Well understanding of all these variables actually is necessary to write a good FEAassist. We say you can learn FEAassist easy and fast, but is it really possible to learn FEAassist simply in a week? If yes, how? FEAassist has many details, variables, and interactions, but do you really need to know all details to solve your problem? Of course not. Only necessary aspects are enough. If you want to learn all aspects and interactions and equations and the functions of the VUMAT, maybe you will need more than 5 years and you don't have this time. So you can save your energy and you can save your time by understanding only necessary aspects to solve your problem. But how? We have prepared for you a VUMAT training package in which you can solve your problem by understanding only necessary aspects. In this package, there are some videos explaining the formulation, the constitutive equation, the relation between stress, strain, temperature, and strain rate. The VUMAT variables are explained in the videos. The whole VUMAT is explained line by line by details in the videos. Any VUMAT needs to be solved by Abaqus solver, then Abaqus model is explained step by step. The result extraction and comparing with the experiments is explained in other videos, and all Abaqus and VUMAT files are also included in this package. This package includes 3 examples. Example number 1, which is a simple VUMAT and most necessary details are explained for the beginners. Example number 2, which is a medium VUMAT and more details are explained for to be more expert. And example number 3, which is a complex VUMAT and almost all details are explained for advanced users. To download this package, you can click on the download link in description or go to our website FEAassist.uk. You need more? You don't have time? And you want your VUMAT to be written sooner? Okay, we can write your VUMAT, test it, verify and validate it with experimental results and teach it to you in videos and online meetings. You can order your project also by the link in description or referring to our website FEAassist.uk. Thank you for your attention. Hello? You want to learn UEL subroutine in Abaqus easily and quickly. UEL is a subroutine to define a new element in Abaqus. Consider you have a one-dimensional element with points A and B. For example, temperature in this element is interpolating between the temperature of point A and temperature of point B. So, a interpolation function computes and defines the temperature in any points in this element. If you want to have more precise solution, you need to add point C and a new interpolation function. Interpolation function can be linear or cubic. You need to define your function in UEL subroutine. For 2 and 3 dimensional problems, it's same. We need to define a new element with a new interpolation function. To well understand these things, stay with us. UEL variables. UEL has some variables. Some of them are inputs. We need to get those inputs, processed on them, and export them as outputs to the Abaqus. In other words, Abaqus computes some variables, which is the displacement of the points, the derivative of displacement of the points, the velocity of the points, coordinates and position of the points, and these variables. We need to get these variables and define interpolation matrix, interpolation function, and the elements, force matrix, variables, and return these new variables, return back to the Abaqus. Again, Abaqus gets these variables and compute the U, du, v curves. This is how Abaqus and UEL interact with each other. which is necessary to well understand to write well-working UEL subroutines. As an example, I explain one of the most important variables here, which is the output of UEL, RHS, right-hand side matrix. Strain is a function of displacement. Here we add curvature for that. K is curvature. Strain and curvature is a function of UE, which is displacement, by a matrix we call B matrix. And when we compute strain and curvature, then we can compute the force and momentum by this strain and curvature with D. D here is a stiffness matrix, or in one-dimensional problems, F equals to D epsilon. D is E Young modulus, elastic stiffness matrix. So this is the Constube equation. Here we solve, by this method, we solve our problem. So RHS is F, which is, by combining these two equations, which is integration in the length of the element or area or volume of the element of BFMDL. So you understand what is the RHS you need to update in your problem. It needs more explanations for A matrix and all the variables. We say you can learn UEL easily and quickly, but is it really possible to learn UEL simply in a week? How? UEL has many variables, many details, but do you really need to understand all details to solve your problem? Of course not. Only necessary aspects are enough. By focusing on your problem, your element, and your formulation, you can save your time and energy. We have done this for you by a UEL subroutine training package for you. In this package, the formulation is explained in a video by details. The UEL variables are explained, something I explained for RHS, for all variables in detail. The whole UEL subroutine is explained line by line in another video. A UEL needs to be solved in Abaqus input file, so Abaqus input file is explained step by step in another video. Result extraction is explained also, and all Abaqus UEL files are included also in this package. This package includes 3 examples. Example number 1 with a simple UEL and most necessary details are explained like RHS and A matrix. Example number 2, it is a medium UEL with more details. And example number 3 is complex UEL in which all details are explained. It is a systematic way to learn complex UEL subroutine. You can download this package by the link in the description or directly go to FEAassist.uk. You want more? You don't have time to learn these things and you want your UEL to be written sooner? Okay, we can write your UEL and test it by published results and teach it to you by online meetings and videos. Again, you can order your project by the link in the description or directly go to the FEAassist.uk. Thank you for your attention.
Hello, you want to learn creep subroutine in Abaqus easily and quickly. Creep is a subroutine to define time-dependent plasticity or viscoplastic behavior of materials. Stay with us.
creep formulation. In creep formulation, creep strain rate is a function of stress, strain, time, temperature, or other variables. This function has some forms. For example, time-dependent creep, in which strain rate is a function of deviatoric stress and time. By entering the parameters A, N, and M, you can predict the behavior by this equation. This equation is very simple, but it is not precise. Other form of creep function is power law function, in which the creep strain rate is a function of creep strain actually and deviatoric stress. Some of the parameters are here. By entering these parameters into the abacus, you can again predict the behavior. Other form of the creep function is sinus hyperbolic function, in which creep is a function of deviatoric stress and actually energy and temperature. You can go to Abaqus, go to property, mechanical section, plasticity, and there you can see creep and swelling option, and in that section you can enter all these parameters and predict the behavior. But mostly you cannot predict the experimental behaviors, and you cannot fit the curves, experimental curves, by these equations. So you need a place to actually write your creep formulation there and force Abaqus software to solve the creep problem based on your new equation, which is not one of these equations. This place is creep subroutine. Creep variables. Creep subroutine has some variables, some inputs and some outputs. Actually, some of these variables are inputs from Abaqus, and in creep subroutine we do some calculations on them, we process them, and we return the new values to the Abaqus. Indeed, Abaqus computes the creep variables, actually transfer the variables, which is time, temperature, deviatoric stress, into the creep. In creep, we need to define the creep strains or swelling strains, the state variables, and return them back to the Abaqus. Abaqus actually again will use the creep strain to compute the temperature, the stress, and these variables, and this loop will continue to solve our problem. This is how Abaqus and creep interact with each other, which is very important and necessary to write a good creep subroutine. We say that you can learn creep subroutine easily and fast, but is it really possible to learn creep subroutine simply in a week? How? Creep have some variables and details, but do you really need to know all details to solve your problem? Of course not. Only necessary aspects are enough. If you want to learn all creep formulations, you don't need them, and you can actually save your time and energy and learn those aspects that you need in your problem. So, based on this, we have prepared a creep training package for you, which is included many things actually in this package that you can easily learn creep subroutine. In this package, all formulations are explained in details in videos. Creep variables, creep inputs, creep outputs are explained, all of them actually. The creep subroutine is explained line by line in the videos, the details are explained. any crypt subroutine needs to be solved by Abaqus software. So Abaqus models are explained in details actually by the videos. And at the end, the result extraction from crypt problems actually is explained in the videos. And all Abaqus and crypt files are included in this package that you can download it. In this package we have two examples. Example number 1, which is a simple crypt in that most necessary details are explained for beginners. Example number 2, which is a medium crypt, more details are explained. And example number 3, which is a complex crypt, all details are explained. You can simply download this package from the link in the description, or you can download this package by going to our website, which is FEAassist.uk. You need more. You don't have time actually to look at this package, and you want your crypt to be written sooner, and we can write your crypt, test it and verify that with published experimental results, and teach it to you in videos and actually online meetings. So you can download this package or order your project by the link in description, or directly going to FEAassist.uk. Thank you for your attention.